All right, in this video, we're going to be solving exponential and logarithm equations. And to get started, let's go ahead and tackle these two problems. For all the problems in here, again, please pause the video and try them on your own first. All right, in answering this question, I mean, obviously we could use a calculator, but let's see what we can do maybe without a calculator. And I see that I can make 1/8. I can kind of treat 1/8 as a power, a number that is 1/2 to a power. So I'm going to rewrite this problem as the natural log of 1/2 cubed, because that would make 1/8, over the natural log of 1/2. And then I'm going to use rule 3 for expanding, and I'm going to rewrite this as 3 times the natural log of 1/2 divided by the natural log of 1/2. And since the natural log of 1/2 is just a number, we have a number divided by a number, which cancels out, leaving us with the number 3. All right, this next one, all of this is the power, so it's e to this very weird looking power. But again, if we take a look at this, this is just 3 numbers being multiplied and divided. This is, believe it or not, like this is just like a times b divided by c. We've got a natural log of 2 times a 15 divided by a negative 3. And so I would suggest we do the 15 divided by negative 3 first. So that's going to give us e to the negative 5 times natural log of 2. And then I can use my power rule, the rule number 3, and get e to the natural log of 2 to the negative 5th power. And then what we hope you remember is that this is e to the log base e, and that is the inverse operation. E log base e cancels out, and we're simply left with what's inside of logarithm. So the answer to this question would be 2 to the negative 5th, or 1 over 32. All right. And again, this is that property that exponents and logarithms are inverses of each other, and so they essentially cancel each other out, leaving us with what's inside. If you're confused by that, go back and take a look at section 3.3 where we discuss that in a little more detail. All right, so here are some very basic equations we're going to play with. Warm-up number 2, let's solve 2 to the x equals 32. So we could write this as a logarithm, but sometimes we can answer these questions without like referring them back to logarithms. We can use a one-to-one property, meaning I can make this say 2 to the x is equal to 2 to the 5th, and therefore we have 2 to the power equals 2 to the power, and the only way that's going to be possible is if x equals 5. So this is that one-to-one property where we know that has to be equal to each other. All right, this next one, we could move the natural log of 3 to the other side. And so then we simply have the natural log of x equals the natural log of 3. And then once again, this is what was called the one-to-one property. And the only way that this can be equal to itself is if x equals 3. All right, on this third one, let's go ahead and rewrite them so they have the same base. So 1/3 is 3 to the negative 1 raised to the x power, or simply 3 to the negative x power, equals, and 9 we can write as 3 squared. So now we know that negative x equals 2, or x equals negative 2. This is once again looking at that one-to-one property. All right. Now, when we get to these next 3, we can't really use the one-to-one property because we don't have e to the x equals e to the something. We don't have natural log of x equals natural log of something. So here, what we're going to have to do is use inverse operations. So we're going to use an inverse on this one. And the inverse, to get rid of an e, we have to take a natural log. So I'm going to take the natural log of e to the x, so taking the natural log of the left side, and I'm going to take the natural log of the right side. We can use our power rule, which brings the x down in front. So we have x times the natural log of e equals e to the 7th. Well, if we focus on the natural log of e, that's just asking the question, e to what power is e, which is just 1. So this natural log of e is 1, so we simply have x equals e to the 7th. Now I want to point out this is the same answer we would have gotten had we just done our switch around rule, right? Our switch around rule of converting logarithms to exponents would be log base e of 7 equals x. Um, oh, oops, I made an error. All right, so on this one, we can't use our one-to-one rule because it doesn't say, e to the x equals e to a power. We have nothing going over there. So what we're going to do in this case is we're going to do inverse operations. So the inverse of an e is natural log. E to the x, the inverse is natural log. So I'm going to take the natural log of e to the x equals the natural log of 7. So I took the natural log of the left side equals the natural log of the right side. I can use my power rule and bring the x down in front, leaving me with this problem. And then the natural log of e cancels out. And so I'm simply left with, the natural log of e is 1. It kind of cancels out, but let's make sure we understand. This part, natural log of e, is asking e to what power is e? And so the answer is 1. So 1 times x is x. So I get x equals the natural log of 7. Now, I want to point out that we could have answered this. This is sort of the formal way. And in algebra, we learn techniques, and most of the techniques are we do an operation to the left side of an equation, and we balance it by doing the same operation on the right side. And so that's what we did here, right? So if it was a multiplication, we do the inverse, which is divide. If it's add, we do the inverse, which is subtract. Just so happens that in this case, the inverse of raising having e to it, the variable power, is taking the natural log. So logs and exponents are inverses. So this is me taking the inverse. Now, let's all be honest. The answer that we got here is exactly the answer we would have gotten had we just used our switch around, turn an exponent into a logarithmic form. This would be log base e of 7 equals x. So that's what we have here. Log base e, or natural log, of 7 equals x. So the result is really the same as just switching it around. So just be aware of that. And for the most part, you can just switch it around if that works for you. But the way I've shown it is the technical way you would do this. And this is me using the inverse. So we have the same issue on this side. We have natural log, which we'd like to cancel out. And the way we cancel out a natural log is with an exponent. And what this is actually called it's called exponentiation, or to exponentiate. So I'm going to use exponentiation, meaning I'm going to do e to the whole side, natural log of x, equals e to the negative third. And e to the natural log of x, again, referring to that rule we used earlier today and the one from the last section, these are inverses of each other. So e and natural log of x cancel out the e and the natural log, and we're left with x equals, I guess let's make it 1 over e cubed. And this would be, again, using an inverse. Once again, we could have got to the same exact answer by just switching it around. log base e, so it's e to the negative third equals x. E to the negative third equals x. All right, so then on this one, we would technically exponentiate, which would be raise the whole side to the 10th power, since it's log base 10. And 10 to the log base 10 cancels out, leaves us with x equals 10 to the negative 1, or 1/10. So we use the inverse again. And once again, we knew that was going to happen. 10 to the negative 1 equals x. 10 to the negative 1 equals x. All right, so let's keep going. So let's apply some of these, either the one-to-one or inverses, to answer the question of what is x. So really just look for the kind of the most efficient way. And in this case, I wouldn't bother with taking a logarithm, because I'm noticing that 9 and 27 have, they come from the same number, the same base of 3. So I can turn 9 to the 12th into 3 squared to the 12th. And I can turn 27 into 3 cubed to the 2x plus 5. Or 3 to the 24th equals 3 to the, I guess I'll just write it like it is. And so this, using our one-to-one rule, meaning there's only one way we can get the same answer by raising 3 to a power, and that is if the powers are the same. So then I can just rearrange this equation and say, when does 24 equal 3 to the 2x plus 5? And now we just solve for x. I could distribute, but I'm going to divide by 3, of course, and get 8 equals 2x plus 5. I'm going to subtract 5, giving me 3. And then I'm going to divide by 2, giving me 3/2. I'm going to check this answer, make sure it makes sense. I plug in 3/2 for x. The 2's cancel, and I get 27 to the 6th plus 5. Nope, 3 plus 5, the 8th power. So I get 9 to the 12th equals 27. Let's do that again. The 2's cancel, and I'm left with 3 plus 5, so to the 8th power. And so are these the same answer? Well, 9, again, is 3 squared. So this is 3 to the 24th. 27 is 3 cubed, so that's 3 times 8. And we get 3 to the 24th. It works. All right, I don't know where this one's going to go quite yet, so let's just kind of see what happens. I'm going to solve this how I normally would. I've got my constant term, so I'm going to move it to the other side, giving me negative 4 x plus 2 equals negative 32. Don't be confused. That negative is never going to be part of the exponent, because remember, exponentials have to be, the x's are always going to be greater than 0 and not equal to 1. And so the negative is definitely on the outside. If for some reason it was included, it would have to be in parentheses. So long story short, I can divide by negative 1, giving me 4 to the x plus 2 equals 32. Once again, I could mess with some logarithms here, but I don't need to, because again, I recognize 4 and 32 come from the same thing. So this becomes 2 squared to the x plus 2 equals 2 to the 5th power. And so I get 2 to the 2x plus 4 equals 2 to the 5th. And the only way that's possible is if 2x plus 4 equals 5. Subtract 4 and divide, I get 1/2. 2 to the 1/2, or x equals 1/2. And we're going to go ahead and just move on, because this video is going to be pretty long as it is. All right, let's try a couple more. So let's solve, write a pre-calculator answer. So if these come out like that, we can't answer them all the way. Answer it all the way up until it's x by itself, even if it means we've still got some algebra to do. And then if we need to use our calculator, we will do so. All right, so let's solve this. Hopefully we recognize what we need to do first, which is to add 3. Get that constant out of there. So that's 5. And then I can divide by 4. So I get e to the 2x equals 5 fourths. All right, so how do we get rid of an e? E to a power? We are going to take the natural log of both sides. Let me give myself a little more room to work with here. So I am going to take the natural log of the left side, and I'm going to take the natural log of the right side. So that'll be the natural log of e to the 2x and the natural log of 5 fourths. Power rule comes down, right? So 2x is now down in front. And pretty soon I'll stop showing that step because I can visualize the 2x coming in front, and then the natural log of e cancels out, making it 1. And so that just gives me 2x equals. I'm going to divide by 2 or multiply by a half. And I get the following answer. So pre-calculator, I have this answer. And then we're going to find the answer and round it to 3 decimal places. So I'm going to do the natural log of 5 fourths, close that, hit enter, and then divide it by 2. And so I get x is approximately, make sure you use your approximately equal sign, to 0.11, and then I'll have to round 111, which rounds up to a 112. All right, part B, I'm going to add the 4 over. And let's see, that's going to give me, add 4 is 15. And then I'm going to divide by 2. And at this stage, I now need to crack into that exponent. And so what cancels out an exponential? That would be a logarithm. So I have my choice here. If I use log base 3, it's going to look prettier. But in the end, I don't know how to do a log base 3. So if this comes down to like a calculator question, I'm going to have to convert it. So let's kind of approach this 2 ways just to illustrate kind of what can happen. So I'm going to do this 2 different ways. I'll use log base 3. So I'm going to take log base 3 of 3 to the 2x minus 5 equals log base 3 of 15 halves. The 2x minus 5 comes down in front, and log base 3 of 3 is 1. Or in other words, it cancels out and I get 2x minus 5. I'm now going to add 5. Oftentimes, we write the 5 plus instead of plus 5, just so there's really no confusion about what's inside and not inside of a logarithm, which is kind of silly, I guess, because if you wanted to, if you put the plus 5 back here, that shouldn't be confusing to people because it's not in parentheses. So logarithm is only of the first thing you come to, but it still helps with the readability for sure to stick that 5 in front. So it's pretty typical to do that. And now I'm going to divide everything by 2, which gives me 5 halves plus, and I'll write it as 1 half, log base 3 of 15 halves. Now, a 3 and a 15 halves, like there's no power that makes this like a power of 3 or anything. So I am definitely dead in the water. I do not know what log base 3 of 15 halves is. So now I'm stuck using my calculator, right? And so in order to use my calculator, I'm going to have to use the change of base. And I could use natural log, I suppose, but I'll use log base 10. So I get x equals 5/2 plus 1/2. And then my change of base formula says that this would be log base 10 of 15/2 divided by log base 10 of 3. And we'll do that on the calculator in a minute. So that was one way. The other way I could have done it, instead of doing log base 3, since I can't do log base 3 on my calculator, I could instead do log base 10. So if I do log base 10 of both sides, I would get log base 10, I don't need to write it, 2x minus 5 equals log of 15/2. All right, let me make sure something feels a little weird here. Yep, I lost my 3. Log base 10 of 3 to the 2x minus 5. Okay, I bring the 2x minus 5 down, put it in parentheses now, because otherwise it'll look like it's just negative 5 times. Still log base 10 of 3 equals log base 10 of 15/2. Notice in this case, we didn't use log base 3, so the log piece did not cancel out. It's still there. So what would be my next step? I would divide probably the log of 3. So I get log of 15/2 divided by log of 3. I would add 5 to both sides. And then I would divide both terms by 2, and I get x equals 5/2 plus 1/2 of log of 15/2 divided by log of 3, which is the exact same place I got right here. So it doesn't really matter whether you get in the habit of just always doing log, or if you do log and then match the base. Sometimes when you do log and match the base, things might simplify out nice and you just get a nice answer. In this case, log base 3 did not help us on this side. So now to solve it, we're definitely have to use the calculator. So we can bypass that whole then change of base formula by just using log instead. You could, of course, use natural log. It does not matter either way. So now to get the decimal answer on our calculator, we're just going to carefully, and don't be the kid who tries to type all of this in. Just do your order of operations. So I'm going to find the log of 15 over 2, and I might just hit enter. So there's that answer. And I'm going to hit divided by, and then I'm going to do log of 3. I'm going to hit that answer. I'm going to divide that by 2 or multiply it by half. And then I'm going to add that to 2.5, which gives me an answer of approximately 3.417. All right. And now let's take a look at this crazy looking problem over here. And I want you to look at this very carefully, because if you look at it and squint and maybe turn your head sideways, you might notice that it feels a little familiar. And if you're like, no, it doesn't, then let me suggest we do a little substitution. So one little trick in math is if you want to make a problem easier, sometimes you can do a substitution. So I'm going to say, let's use z, any variable you want. I'm going to use z equals e to the x. And now let's take a look at this problem again. E to the 2x, well, I said z is e to the x, not e to the 2x. So what do I do with that? Well, e to the 2x could mean e to the x, the quantity squared, because power to a power we multiply and we'd have 2x, minus 4e to the x minus 5 equals 0. Now, if I do my substitution, e to the x becomes z, so we have z squared, minus 4 times z minus 5 equals 0. And this, of course, is a quadratic. And so I'm going to factor my quadratic to solve it. And we'd have a 5 and a 1, a negative 5 and a plus 1. So I set each factor equal to 0. And I get z equals 5 or z equals negative 1. But of course, the problem isn't z equals, it's e to the x equals 5 or e to the x equals negative 1. And so now, to solve this, I need to figure out what x is. So I would take the natural log of both sides or just switch it into logarithmic form. And I would have x equals the natural log of 5 or x equals the natural log of negative 1. So this is what's known as a quadratic form. And if you can see it and do it without doing the substitution, then go right ahead. But for some of us, it's easier to just get that e to the x out of there, and then it becomes pretty simple. Now, the only other thing we really need to be careful of is because as I wrote down the answer, there was a little warning light that went off in my head, and hopefully some of you noticed it as well. We kind of have a problem right here. I'm telling you that there are two answers. One of them is the natural log of 5, and the other one is whatever the natural log of negative 1 is. Well, the natural log of negative 1 is impossible. There is no number e to a power to get negative 1. E to a power will always be positive. So this is, of course, what we call extraneous. So we would not consider this an answer. We would consider extraneous. But please make sure you show me your work. It's not like you accidentally missed it. Like there are some problems where if you do something like wrong up here, you might get this answer and never get this answer. And just because you made a mistake and got lucky is not the same of doing it right. So make sure you get all the answers and then consider them and see if they actually both work. Oh, and that one does not. So then we scratch it out. All right, we got a couple more to do here. Again, I told you this would be a long video. All the previous problems, the previous three, all started as exponentials. And so we had to use logarithms to solve. So now we're going to do a couple examples where we'll start with logarithms. And so we'll probably have to exponentiate to solve. All right, so part A, very simple one. Again, this would be an exponentiate situation, or just switch it around, but we're going to do it the right way. So I'm going to take e, because that's the base of the natural log, e to the natural log of x equals e squared. E to the natural log of x cancels out, and that leaves us with x equals. This is the division to the multiplication. E to the natural log cancels each other out. And I get e squared as an answer, and we're done. If I'm going to use my calculator, then I would, of course, finish that. In fact, we'll go ahead and do that. Most of the time, answering to z squared would be perfectly fine, but we'll go ahead and follow the same directions as the previous problem. Let's round to 3 decimals. So I'm going to use my E button, and I get x is approximately equal to 7.3890. So 789. Or 389. All right, on part B, we don't have to do anything terribly fancy because if we look real close, we see that they have the same base. So log base 3 equals log base 3. The only way that's going to be possible is if the insides of them are in fact the same. So we can just sort of dump the logarithms all together and just figure out where the inside is equal to 0. Subtract x, add 1, x equals 2. Let's make sure it's not extraneous. I plug in 2 and I get 10 minus 1 is 9. That's fine. Plug in 2, I get 7 plus 2 is 9. Log base 3 of 9 equals log base 3 of 9. It works. All right, and now let's try this one. Let's isolate the logarithm piece. So let's subtract 5 over. So I get 2 natural log of x equals negative 1. I'm going to divide by 2. Natural log of x equals negative 1/2. Technically speaking, at this stage, I'm going to exponentiate. So I get e to the natural log of x equals e to the negative 1/2. E natural log cancels out. I'm left with x equals, I guess it would be, we'll just leave it like this, I suppose. Technically speaking, if I'm going to go to a calculator, it doesn't really matter. But really what this problem would then be is x equals 1 over the square root of e. The negative flips it over. The 1/2 means square root. But I'm not supposed to write square roots in the denominator. So if I was going to leave this in the best form, I would rationalize by multiplying, and I'd get root e over e. But if I'm going to just use my calculator, then who cares? Let's just use our calculator from here. And once again, I will use the e button, and I'm raising it to the negative 0.5 power, which gives me an answer of approximately 0.6065, so 0.607. If this was a test question, we would leave the answer right here. But honestly, probably I wouldn't probably penalize you if you left the answer at any of these stages. But strive for the best. That would be the bottom answer. All right. So speaking of extraneous solutions, here's a couple more with some extraneous solutions. Okay, so how are we going to answer this question? Notice the old switch around method's not really going to work right now because it's not just one single log statement by itself. So it's not just like 3 to the power of 2 equals something, because what the heck would it equal? So this is where using our condensing formulas is going to pay off. So before we try to solve this and do operations on each side or switch it around, we're going to need to condense into one logarithm statement. So this is going to become log base 3 of, it's plus, so these are going to turn into x times x minus 8. So all of that is now inside log base 3 equals 2. So now if you want to do the old switch around, go ahead. I'm going to practice using, come on, pen. Thank you. I'm going to practice doing it, quote, the right way. So I'm going to exponentiate on both sides. So I'm going to exponentiate with a 3, meaning I'm going to do 3, and then all of this nonsense becomes the power. And on this side, I'm going to have 3 to the power. 3 log base 3 cancels out, so I'm left with just x times x minus 8 equals 3 squared is 9. And please don't do anything crazy here. We should recognize at this stage, this is simply a quadratic. So in order to solve a quadratic, we need to set it equal to 0. So I have x squared minus 8x, distribute the x, and let's move the 9 over. Now I will factor. And we've got simply a negative 9 plus 1. So x equals 9 or x equals negative 1. Because we're working with logarithms, we have to be very careful because we have to make sure these answers work. So let's take our 9 and come back up. And I'm not really looking to make sure it works. I'm just looking to make sure it doesn't cause a problem. Log of 9 is not a problem. 9 minus 8 is 1. That's not a problem. So 9 is fine. But if I plug in negative 1, I get problems all over the place. This would be log of a negative number, which will not return an answer. And this would be log of negative 9, which also would not return an answer. This one does not work. All right, let's take a look at B. Once again, I think condensing makes a lot of sense. And I'm going to condense these together, which would give me x plus 1 over x minus 2 equals natural log of x. I could, if I want to, move that other natural log over and condense that as well, equals 0. But at this stage, we don't really need to do that because we're at that one-to-one stage where natural log of this and natural log of this are equal. So the only way that's possible is if x plus 1 over x minus 2 equals x. So to solve this, we are simply going to get rid of the denominator. So I'm going to multiply both sides by x minus 2, leaving me with x plus 1 equals x squared minus 2x. So we still have a quadratic situation. So I'm going to get everything on the same side. So I'm going to move everything to the right side. So I get 0 equals x squared minus 3x minus 1, I believe. Let's just check that math. Looks good. All right, I've got a little issue here, and that is does not factor. So to find my answers at this stage, I'm going to have to use my quadratic formula or complete the square, whatever works best. I'm going to go ahead and complete the square simply because I haven't done it in a while. I want to practice. So I'm going to switch sides too. So x squared minus 3x equals, I'm going to move the 1 to the other side, making it positive. Half of 3 is 3 halves. So I'm going to square that. So I'm adding in a 9/4. And I'm going to add 9/4 to the other side as well. So that gives me x minus 3 halves squared. Let's see, 4/4 plus 9/4 is 13/4. And so then I take the square root, which is going to give me the square root of 13 over 2 plus and minus. And so I get an answer of x equals 3 halves plus or minus root 13 halves. Okay, let's go take a look at our possible answers. First of all, x is going to have to be a positive number or we're in trouble. Also, x has to be a number that is bigger than 2 because otherwise I get 2 minus 2 is 0, and that's a problem, either because it's 0 or it becomes negative if it's less than 2. X has to be bigger than negative 1, but we already just said x has to be bigger than 2, so we're kind of covered there. So as I look at this problem, the square root of 13 is 3 point something. And so 3 halves minus 3 point something halves, that's going to be a negative number. So I already know the negative doesn't work. And so the only answer would be this one, as long as it's a number bigger than 2. And it is, because this is a 1.5 plus something bigger than 1.5. And so there is our only solution. It's an irrational number. And if we wanted a decimal, we could find it. But I think I'm just going to leave it for it now. Okay, we are on the home stretch. The last questions I want to do here is let's kind of pull the solving into context with graphing. So find the x-intercept of the function. So let's practice two things here. First, let's graph this thing. Ooh, way too big. Let's use smaller squares. All right, so what is this thing going to do? it is going to be a parent function of 3 to the x. It's going to be twice as tall and flipped upside down, as well as some shifting. All right, so let's get it shifted. 1, 2, 3, 4, 1, 2, 3, 4, 5. So it's shifting up to here. And so I would expect at this stage, 2 to the x looks like this. I'm sorry, 3 to the x looks like this. And then twice as tall would just be a taller version of this, but the negative is going to flip it over. So I should have a graph that looks like this at this location. So now let's get accurate. I know that normally is a y-intercept, which would be 1, but now it's going to be doubled, so 2, but it's negative 2. So it should be right here. I would normally go over 1 and up 3. This time I'm going to go over 1 and I'm going to go down 6. 1, 2, 3, 4, 5, 6. We know we're over 1 this way and down a third, but actually down 2/3. We have an asymptote right here. So my graph looks like this. So now I want to find the x-intercept. So we know that the x-intercept is found, no matter what the function, by setting it equal to 0 and solving. So now I need to solve the equation. So what am I going to do? I'm going to move the 5 over. I'm going to divide by negative 2. So it becomes a negative 5, but then dividing by a negative 2 makes it 5 halves equals 3 to the x minus 4. At this stage, it's logarithm time. So I'm going to use natural log just because it'll work and it's easier to write. So natural log of 5 halves equals the natural log of 3 to the x minus 4, which is the natural log of 5 halves equals, bring the x minus 4 down, natural log of 3. I'm going to divide by the natural log of 3. Oop, jumped on me. So that's going to give me the natural log of 5 halves divided by the natural log of 3 equals x minus 4, or x equals 4 plus natural log of 5 halves over the natural log of 3. And I'm going to grab my calculator. And I hope the answer is somewhere in the neighborhood of 1, 2, 3, 4, very close to 5. Let's find out. All right, natural log of 2.5, enter, divided by natural log of 3, and then I'm going to add 4. So I get x is approximately equal to 4.8340. So let's write it as a point. 4.834, comma 0. I didn't ask this, but we're here. We might as well do it. What's the y-intercept going to be? So the y-intercept is always found the same way. Take the function and set it, or plug in 0 for x. So we've got f of 0 equals negative 2 times 3 to the 0 minus 4 plus 5 power. So we have negative 2. 3 to the negative 4th is going to be 1 over 81 plus 5, which gives me negative 2/81 plus 5, which I know some of you want to grab your calculator here. But if I'm taking away 2/81 from 5, well, that's a lot less than 1. So I'm still going to have 4. And then I'm going to have, if I took away 2 out of 81, then that's going to leave me with 79 out of 81. And so my y-intercept is going to be 4 and 79/81. Let's make sure that makes sense. 1, 2, 3, 4, very close to 5. Our asymptote's at 5. We're getting very close to 5 already. This makes sense. This is the point, 0, comma, 4 and 79/81. And our last one. My computer is tired, so it wants to be done. All right, so this time we're doing a logarithm graph. Let's graph it first. Let's figure out what it's going to do. It's going to shift in the positive direction and down and go up. Okay, so I'm just trying to figure out where my axis should go. So it's going to go down. So let me give myself some room here. Okay, shift over 4. 1, 2, 3, 4. Down 6. 1, 2, 3, 4, 5, 6. All right, so there's my new location, and my asymptote is right here. And I'm just going to go ahead and add a dotted line here, not as an asymptote, but just as a guideline to help me out. Okay, this is a logarithm that's base 2 that's going to be stretched 3 times as tall. So my intercept, fake intercept, is 1, 0. Then I'm going to move over, since it's base 2, I'm going to go over 2, and I would normally then be up 1. Except this is 3 times as tall, so I'm going to be up actually 3. Then I would have to go over to 4 to get to an answer of 2, but now my answer of 2 is going to become an answer of 6. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And so my graph is still a logarithm. It's still bending out. It's just not bending quite as quickly. It's growing faster because we have the times 3. All right, let's see if we can algebraically confirm that this is the answer, which is 1, 2, 3, 4, 5, 6, 7, 8. So the graph tells us we're at 8, 0. Let's see if the algebra tells us the same thing. So the x-intercept, we're going to let g of x equals 0. I'm going to add 6 to both sides, and then I'm going to divide by 3. So add 6 divided by 3 makes it 2 equals log base 2 of x minus 4. I can exponentiate or just switch around. Either way, I'm going to be left with 2. Computer froze on me again. Hold on. 2 squared equals x minus 4, or 4 equals x minus 4, and obviously I get x equals 8, which is what we got algebraically. There's no need to find the the y-intercept because we never are going to get there. Okay, thanks for hanging with me. If anybody made it to the end of the video, this was solving equations. And if you have questions, let's talk about it in class.